Hello and welcome everybody today for our first Creotech Instruments webinar. We're live from Warsaw. We're very glad that you found the time to join us today. There will be also time at the end of the webinar to ask questions. If you have any questions along the way, you can write them down on the chat window. My name is Zofia Olszewska, and we have with us today Grzegorz Kasprowicz, who will present our Sinara ecosystem and booster. Also, he will also talk about boosters. And then we'll move on to Paweł Kulik, who will tell you something more about Arctic software. And after that, the last part of today's meeting will involve the questions and question sessions, and will be led by Przemysław Kowalski. So once again, thank you for joining us. And Grzegorz, if you could please start with your presentation.
Okay, so hi all, good morning. My name is Greg Kasprowicz, and I'm working at Creotech. Actually, I'm one of the guys who started Creotech in 2008. So now it was we started in a garage, and now it's a company which has 220 or more people full-time working on this fascinating technologies. And today I also work at the Warsaw University of Technology. Some of you know me from this side. So today we'll talk about the Sinara. I will introduce you to this ecosystem. Some of you probably use this system. Some of you never heard of it. So I try to be quite general. I will talk about what we have and what we are working on right now, and then we will have a discussion. First, a few words about Creotech Instruments. So we are recognized mainly as a space company. So we build space electronics also as a service, but we also have a quantum. We also work in the field of quantum. Actually, we don't build quantum computers, but we focus on instrumentation for quantum systems. We have a few interesting projects right now. Some of you may be interested. First of all, we're building a shuttling system for European 1000-qubit quantum computer, and we have also built several other instrumentation like qubit readout cameras, lasers. We are integrating quantum computers with supercomputers, and recently we work on a satellite and the ground quantum key distribution. But let's talk about the Sinara. Why Sinara and why this project started? Now, if you look at the typical quantum lab, this photo shows a lab at NIST. You can see that there is a lot of unique, dedicated control and measurement equipment, each from various brands, some made by PhD students. Most of this equipment have some non-typical interfaces, maybe not from hardware, but from software point of view. And it's very hard to recreate same conditions in other labs. If you cooperate, we have two labs cooperating with each other. It's very hard to make exactly the same setup, having the same AWG generators, the same laser drivers, etc. So, this is the example. I was some time ago. I was in Colorado, Boulder, visiting this GILA lab, and in each lab, in each group, there was this poor guy or carving his own DDS, DAC, and digital I/O, AOM driver. And when I ask, why do you build your own DDS? Your colleague next door is building. Mine is going to be better. that guy doesn't want to have share the documentation, or it doesn't work in my conditions, etc. So this is why the first Arctic was founded. It was founded by guys from East and Maryland and Oxford. And then my team joined and started building nice industrial grade hardware. So what is Sinara now? Sinara, after I think it was 7 years of development, we have already over 50 modules which are commercialized. We created over, I think now we are close to 90 various modules, but some of them were used for testing. Some of them were simply discontinued, like micro TCA approach, or some of them were simply outdated. So we have something like 50 different modules which are available. And we decided to use low-cost Eurocard approach. Of course, it has some drawbacks and also advantages. It's low cost, first of all, and that's why recently we are slowly migrating into something which is more industrial, like we are talking about DIoT. I will talk about it later. So this EM, it's your card extension module, defines connector and signals and power budget and front panel and such a things. For the moment, we are developing something. I think we are continuously developing something like 10 new modules since I remember. So with this Sinara hardware, we address various needs of quantum applications, starting with RF generator, qubit readout, qubit ion atom positioning, shuttling, DC biasing, field stabilization, laser tuning, laser noise removal, fiber noise removal, temperature control, etc. Essentially, whatever is needed in the lab, we can do it with Sinara. There are very few applications where we cannot propose Sinara solution to it. And as I said, Sinara wouldn't exist without Arctic. Arctic is essential part which ties together all this Sinara and non-Sinara equipment, and yes, and Sinara is interesting project because it presents bottom-up approach. It was defined by customers and founded by society, by the scientific society. So the several institutions like NIST and Maryland and Duke, Oxford started founding hardware and software development. Others quickly followed, and we used a lot of public funding at the Warsaw University of Technology to actually build this hardware. So we started with a few boards, and then we got inertia, and now have a lot of funding and can make new exciting developments continuously. So there are several institutions behind this project. I don't have to probably explain why ion traps are interesting, because I think most of you are from this ion trap field. But for the others who first see this presentation or this system, ion traps are interesting because they are ideal. I mean, these ions are identical. So you have two calcium ions and strip the electrons. They are just perfect twins. So we can make very good qubits. We can use it for metrology, atomic clock, mass spectroscopy, simulation, quantum computing, a lot of other interesting applications. And for all of these applications, of course, need instrumentation. So as I mentioned, for ion traps, first of all, we need very good synchronization, very low noise in order of some nanovolts, very good phase noise in terms of RF signal generation, and very good DC stability. So this is where we jumped in as a Warsaw University and proposed the hardware which solve this issues. So let's to start. Sinara is system consists of Paweł will tell later about the architecture in the next presentation. It consists of two components at least. We need a system controller and the peripheral board. You know, some people call it the system controller as a core device because it's a I'm talking about in a general form as a system controller, but the core device is a it's an Arctic name. So before the moment, we have several system controllers. The historically first was Arctic 7 Castle. These names, some of you may wonder where these names come from. At the very beginning, when we had just 4 boards, the guys came with idea. Let's call these boards names of Russian lakes. It was before 2022. And then once we had started having more boards, nobody knew what Novogorny is doing and what Zotino is doing. So we started calling boards in a way that it somehow is related to the functionality. So the shuttler is shuttling, sampler is sampling, etc. Pounder is doing PDH, etc. So we start. But we left this board for historical reasons because people already got familiar. So Castle, as I said, Castle 7 was first one. Then Castle SOC arrived. But some people want to use this crates outside of this Castle ecosystem. I mean, they want to develop their own gateway using their own preferred controller. So we can also use this Castle, this EM modules in outside of the Castle ecosystem and Arctic ecosystem. So you can either take Castle FPGA controller and write your own software, or gateway and software, or you can use it outside connecting to any carrier boards which has FMC connector like KC705, and for this purpose we developed such a pair of modules like VHDCI EM carrier. VHDCI because we use low-cost VHDCI cables which are useful in SCSI systems, and with such a board we can control our modules in outside of this FPGA board, which you will really plug to your PC. The other place when you use this EM carrier module, you can take some, if you want to put some Castle peripherals in the second crate, so you can take pair of this EM carrier modules and just make the second chassis with modules connected to the same Castle. Currently, you are working on other controllers. It's one is dedicated to DIoT. It's Zinc Ultra Scale. It's actually it's a product, but it's not ported to Arctic yet. Another one is this TM system board. It's a low-cost system for non-real-time applications in a place where you don't want to have Castle to control the temperatures. You can use this STM system board. We use it mainly for RF amplifiers and some DC voltage distribution systems. Another modules which are peripheral modules are ADC and AX. So the historically first was sampler. It's a 1 mega sample 16-bit ADC with very universal input. You can have it from 10 millivolts to 10 volts input range, and you have switchable termination. And it's nice because it has 1 mega sample in each of 8 channels. Another one, which was initially developed for ion traps, is Fastino. It's very low noise DAC. Actually, it was Zotino, which was low noise DAC. But it has this disadvantage that it has a update rate of 1 mega sample or something per 32 channels. So it's good if you need to provide static electric fields. If you want to go for shuttling, we have a Fastino. So it's a 32 channel, 2.5 mega sample per second DAC. with a gateway which provides good ability to do interpolation. So you don't need to transfer all the samples with full speed through the host. You can simply transfer every n sample, and FPGA gateway would do the rest. So it's nice when you need to do a lot of shuttling in your IO trap. I was at the ECTI conference recently, and a lot of groups are working with shuttling. So this Fastino is a good choice. We also have a booster, I mean the amplifier which boosts the Fastino outputs to plus minus 555 volts. I will talk about it later. And currently under development we have a shuttler, which is 16-channel board but it has different philosophy. The Fastino generates signals at the source, and then you need to have these long cables which deliver it to the trap. Shuttler is optimized for very low noise operation and for much faster operation. So the front-end board, front-end module is placed directly at the trap, close to the trap, to limit the capacitances, and that's why we are able to achieve much higher update rate and much lower noise, because first of all we have fully differential signaling between DAC and the front-end the output amplifier, and also because we keep much lower impedances. We are essentially, the system is 50 ohm most of the time, so the noise coming from resistances is much lower. This shuttler comes with EM FMC carrier. This carrier is a example of the card which is dual system. You can make it in EEM with ribbon cables, but you can also order it or just install connectors which you press fit. You don't have to solder, then we need to have tools. You press fit the connector and can use in this backplane version. I will talk about it later. So we are slowly migrating all our modules to this backplane version, but we keep compatibility with these ribbon cables in both ways. So even if you have ribbon cable version, you will be able to later use with this backplane version as well. This carrier is foreseen for several boards. So it doesn't make sense to develop all the modules, especially ones which are not producing a very high volume, to have onboard FPGA. So we simply use FMC. It has also advantage that you can use a lot of FMCs from the market, which are already available and low cost. For example, many analog devices, Texas Instruments, ADCs, and DACs are already in FMC form factors. You can simply plug and use it as they are, and they are very cost effective. Then we have generators. We have for the moment we have a Urucool, which is a 1 gigasample DDS and quad 4-channel DDS module, which has very good spec. It's very well characterized. It's very low noise. It's mainly used for lasers, for AOM driving. It has two flavors. One is 9910, another is 9911. They have slightly different characteristic. One of them is able to synchronize channels between not only channels in a module, but you can also synchronize multiple channels in the crate. And then we have a Mirne microwave synthesizer. Mirne is output channels work up to 4 gigahertz, but if you want to have 13 gigahertz, this error, it's actually the Almaz, the plug-in module, it works up to 13 gigahertz. So if you want to have more than 4 gigahertz, you can order Mirne with RF mezzanine, which provides much faster output, much faster analog chain. And of course, we have a clocker. It's a 10-channel low jitter clock distribution. One thing, recently we updated this clocker to drive optical lasers, which needs more power. Essentially, what you need to do is to simply change resistors values. If you need more output power from clocker, you essentially need to install lower value pull down resistors, and then you will get Pavel, correct me if I'm wrong. It was what was the output power you can get from clocker?
So over 6 dBm.
Yeah, so you can get 6 dBm easily just by placing different resistors. So we are not even going to make an assembly variant. You can just we want to make some outputs as with higher power. Uh, Then we have arbitrary waveform generators. We started with the SIMA, some of you may know, but it was very expensive and it was overkill for ions. So actually, it was produced, it was characterized, it was supported by Arctic, but at a certain moment, well, we developed phaser, which is much lower cost and it is good enough. So this SIMA was discontinued, but if somebody wants to use this project, it's well debugged and the hardware is there, and we can or you can use it at least as a basis for something new. It's all of course on the repository. And then you have a phaser. Phaser it's exists in two flavors with up converters and without up converter. With up converter, it has two IQ paths and it works up to 4.8 gigahertz. And without up converter, it can be used as a four-channel single-ended output. And this phaser also has 5 megasample programmable ADC like in a sampler with this universal front end. Currently, we on we if you like base one thing the phaser has a new firmware coming. It's called Mini. It means it's a much improved version comparing with existing one, we can have many tones and independent amplitude shaping. It's Quartic who develops this firmware. It's unfortunately not open source, but if you need some sophisticated control, you can ask them to provide the gateway as a yes as a compiled block essentially. And so yes, and now in the development on the same, we built a waiver. It's a 4-channel AWG, which works with this FMC carrier uh, here. And it's essentially it's a phaser. From gateway perspective, it's a phaser, but it has a DC output, DC coupled output, and can produce 10-volt peak with 50 ohm termination. So and has a programmable bandwidth. So it has also 4 channels. So it can be used for all the applications. It needs much higher, uh, much stronger output and also DC coupling. But this is the feature which so you can program. You can just if you need to, for example, to control some trap electrodes or something like this, which needs to have both AC and DC capabilities, this is the way to go. As you see, the board exists. We are now working on production test suits because that there is one thing which I should mention. All this hardware was developed by the Warsaw University of Technology using public funding. So because it's public, the government or the European Commission makes the funding. So we place it on open access on a GitHub. But these are just prototypes. So if you want to turn prototypes into product, so this is the Warsaw University does half of the job. Another half is to convert this to products. I mean, to make test benches, to make this production environment, testing equipment, all this characterization and support and guarantee also. So this is so if I say something, this is under development. It means it's the hardware is usually there, and we are working on test benches. But I cannot say exactly when it's going to be available. It depends on a client request, and if clients are interested with certain module, we speed up development. If clients are not interested, we simply let it go with our I mean that they will keep a lower. We don't put so much priority on it. And currently working on a RF SOC as a smart arbitrary waveform generator. It's mainly for low latency applications when we pair this IWG with supercomputer. This is one application. Another thing is for ones who are not fully satisfied with the phasor up converter. So with RF SOC, you can go much higher with phasor, and in some application don't need the. You can make this you can get rid of this analog up converter and convert this generate signal using digital up converter, which should be much less, should have much less noise. In the meantime, we are working on FMC mezzanine with 12 gigahertz DAC. I didn't show it here, and this is yet another approach where we can get much better noise characteristic than the RF SOC, especially not only noise but also crosstalk. RF SOC is known of its quite high crosstalk between channels. Then we have another group of modules which are control loops essentially. So we have a historically first, it's a stabilizer. It's a 2.5 megasample PID controller. It can be paired with mezzanines, and it has very universal input. So it accepts from 10 millivolts to 10 volts at the input. It can be placed in a chassis. It can work standalone, supplied via power over Ethernet or DC wall wart. So it's very, very universal. Guys are using it for pound level hole log generation. They're using for magnetic field stabilization, especially using LEM sensors. Some other are used for ion trap frequency. Ion trap driving RF field stabilization. I know labs which managed to get to 1 ppm using stability using this stabilizer, so it's very well debugged and major product. Then you have a thermostat. It's a two-channel temperature regulator. Guys, it's known to provide temperature stability to some microkelvins. It can work standalone. It can work as a EM module supplied with 12 volt DC. It can work with power over Ethernet, so it's very versatile. And we also developed four-channel version of it, which stronger drivers and with more versatile front end, which works on also with cryosensors. So this is thermostat EM. Boundary is a two-channel pulled over whole log generator. Robert Jurgens from MLab from Quartic wrote very, very good firmware. Advanced firmware which makes to the extreme the stabilization and this PDH locking. And then we have a fast servo, which is currently under development. As you see, it exists as a hardware. We have it now. It's ported to Arctic. It's also we have an alternate firmware which uses a known library. Pavel, can you remind me what was the library for fast servo which we ported?
Sorry, from the top of my head, I can't remember.
Yeah, so this is the library used by laser guys, and for interferometry. I can write it down once I remind myself what was it, but very very popular environment. It's like red pitaya for lasers. So
I think it was Linian.
Yeah, exactly. So yes, and then we have a lot of digital I/O modules. So with I/O, with SMA, DIO, MCX 16 is non-isolated, but it's faster than these isolated ones. J44 is one dedicated to SPIs. People use this each of the module or each of the plugin as a dedicated SPI sensor or extender or whatever. It's also you can use this module to extend the EM over the lab. If you want to place one EM module on the other side of the lab, you can use this one using for Ethernet cables. And now another development, we have isolated DIO, which all the channels are individually isolated. It's foreseen for the IoT platform. Then we have several adapters, like Grabber, which is camera link board. We have some various adapters which make Zotino, Fastino fan outs of these connectors. No, but not everybody wants to use these SCSI cables. If you want to use SMAs or BNCs, you can use like 4 such adapters and make a fan out. If you want to, for some reason, make this fan out in another crate, you can make HD60, this SCSI cable, place this HD60 to ADC, and then several modules with SMA or BNC cables. And recently, under development, we have this passive channel breakout for Fastino Zotino, when you can take it, place it on your optical bench and connect MCX or BNC connectors directly. So we don't have to put all this, pull all these cables along the lab. And new development, so for bigger ion traps, which need higher voltage, essentially for ion traps at CERN, for antimatter, we developed dedicated modules, which is HVM32. It's 32 channel, 50 volt booster for Fastino and Zotino. Now we are working on a lower noise, something like 10 times lower noise than the one version on a GitHub. We are working on for this European quantum computer. And then we have this 200 volt. It's a 200 volt, 1 megahertz, but 1 megahertz is a low power bandwidth. It's 8 channel, but it's powerful amplifier already with DC-DC converters on board. It's used mainly by CERN. I mean, it's a primary user, but you can also use to drive some piezos, because we're using this Apex amplifiers, so they are designed for this purpose. And also under development, we have a 2-channel floating high voltage power supplies. They were developed mainly for gas electron multiplier detectors, but I think we can use them also for other applications, like to supply high voltage DACs, for example, which also working on 1 ppm high voltage DAC for ion trap electrode. Yeah. And then we have several accessories under development. Digital photodiode it's a project. It's a very small project, but it takes already a lot of time. It was started by my student, and now it's trying to make it a commercial product. At the beginning, it was with Ethernet. Now we switched to single pair Ethernet, so we can use one a twisted pair to connect several such digital photodiodes. It has very high dynamic range, and can work with either linear or logarithmic amplifier. And as I said, it works with you can use analog output, and you can use USB interface, or you can use this single pair at Ethernet, so you can have something like 20 photodiodes connected using one single pair routed across your system, and then have one router which routes to standard Ethernet connection and power over Ethernet. So you can connect the power over Ethernet ecosystem. And then last development, which this board was assembled a few days ago and made running, it's a Fastinobooks. Actually, when you build a cryogenic setup and have several connectors, filters, and a lot of stuff in between Fastino and your ion trap, it's prone to errors. I mean, during cool down, your resistors can crack, the connectors can lose contact, and there are lots of issues which can appear. So we developed the multiplexer, diagnostic multiplexer. You can connect network analyzer to these input ports, and actually you can connect 2 network analyzers, and you can then run tests. So you can choose which channel to disconnect from the Fastino and connect to the network analyzer, or and you can also inject and measure the crosstalk between any 2 channels. That's why we need two groups of relays, so we can connect either the network analyzer or impedance meter between any signal and the ground, or we can connect this impedance analyzer between any 2 signals. So you can measure crosstalk during cooldown, during operation. If something doesn't work, you can run a full diagnostic of your quantum computer during startup to make sure that all this signal integrity is kept and all these low pass filters close to the trap have correct values. The resistors didn't crack during cooldown, the capacitor didn't crack during cooldown, and all the joints are in place. So this is we are using actively for our quantum computing project at the Warsaw University of Technology and also in Creotech. And then I mentioned the DIoT a lot before, and the IoT is a CERN standard. Standard. It's not standardized per se, but it's based on a compact PCI serial. So actually, the standard is compact PCI serial when we use entire chassis with power supplies, fans, backplane, etc. Because it's existing, you can buy from several vendors. It's quite cheap, and in the meantime, we made open hardware version of it, which is adopted to requirements of high energy physics. So you have this remote power control. You can reboot this crate remotely using some BNC cable, and has redundant power supply. So now we are working on the integration of Sinara. So all the new modules, Sinara modules have or new revisions have a DIoT connector, place for the IoT connector. So you can always either order in the DIoT form factor, or you can make this install connector yourself and just put a few jumpers. So you don't have to remove these EM connectors. So you can make it, or you can, if you have some old module, you can also order an adapter which will adapt to the IoT. The IoT solves several issues. So, because when you have your Sinara control system in the lab, that's fine. You don't need to carry it. You don't need to ship it. You don't reconfigure it. You don't need this CE certificate, etc. And so this DIoT takes this scenario to the next level, makes it more ruggedized, fits into existing standard. This compact PCI serial is used, for example, in the railways. People use it in space even. There is version of space one. So you can make benefits of this these chassis which are designed to withstand vibration, shock, and etc. So one thing is of course it uses backplane instead of this ribbons. It uses much better clock distribution without it doesn't need clocker, and it solves the issue with cooling, so we don't have to attach a fans below your crate and pray that the modules don't overheat. And first of all, it provides correct sequencing, because the problem with existing Sinara ecosystem is that if some of the module wakes up or is supplied from other power source or wakes up before Castle, it may happen that it outputs DC signal on this LVDS line, and it may lead to provide supply to this Castle bank before Castle board, Castle power supply system wakes up. So this may cause to unexpected issues, and this in this DIoT chassis we make a power sequencing depending on a slot. Each slot has a geographical address, and the system controller wakes up first, and each next module counting from left to right wakes up after several milliseconds. So this way, this issue should be fully solved. Of course, we need to make tests. That's why it's under development. You can see the hardware, it's working, but of course, it's under development because we want to make sure everything is perfectly working before ship to the customer. Another thing is we are working is a Castle DIoT. For the moment, we made adapters. We call it Franken adapter because it's some Frankenstein monster with this Castle board sitting on it, but it's only for development to make sure everything works. Then we make a dedicated DIoT Castle controller. So we are not going to sell these adapters pretty soon. If somebody is very stubborn, wants to have it, of course we can talk, but we don't want to support it because these connectors are very messy. And then, as I mentioned, we developed this adapter. So this adapter essentially have this sequencing logic, some JTAG logics, because in this BIoT, there is option to expose JTAG interface of the peripheral modules to the controller, so you can make JTAG debugging. But it's a long. It takes some time before we support it. It's not supported in Arctic yet.
Grzegorz, can you please move on? Oh yeah, thank you very much.
Yes, so now we want to talk about RF amplifiers. It's another group of products which are not related to Arctic or Sinara. They are used with Sinara ecosystem intensively, mainly in this intensity SU servo, which is this sampler Urucool servo for laser stabilization. We have, for the moment, two versions of boosters. Historically first is a high efficiency, so it provides, well, quite a lot of harmonics, but at the price of high power efficiency. So it's something like 60 to 70% power efficiency, depending, of course, on the power at the output. And it provides up to 5 watts per channel. It has a lot of advanced monitoring and protection system. It's a temperature control, interlocks at input, output, and reflected power, so you can program it to protect your optical modulator. They are control over Ethernet and MQTT, and it has two open source firmware options. It's this legacy Sinara and also Quartic. They have slightly different philosophy in the approach. The first one is written in C++ and C++. The second one is written in Rust. It's supposed to be much more stable and reliable. But it's still under development. But you can download versions, and it's very actively supported. The Sinara firmware is not really supported. We developed to a certain level and then switched to this Quartic version, but it's still available. Some people like it. It doesn't have any serious bugs so far, as far as I know. But this Quartic firmware takes it to next level. Before it was available on a license when you had to pay for it. Now it's released on open source, so you can use it essentially and upgrade it yourself. And there's another booster which was introduced 2 years ago, I think, or 1 year ago. This booster is optimized for high linearity. It's very linear up to 1 watt. It's for 1 watt. It has minus 40 dBc for second and third harmonics. For 2.5 watts, it's something like minus 30. It works between 40 and 800 megahertz. Of course, it depends how you define the 3D bandwidth. If you work only for certain frequency, it can go even to 1 gigahertz and down to 20 megahertz. And as I mentioned, it consumes a lot of power, but of course it has a very good linearity. It is used mainly for qubit operations. Booster can be configured up during order, so you can choose make standard or high linearity or mixture of both in one same package. You can ask for firmware, which is this legacy C++ open firmware, or you can ask for this Quartic firmware, which is based on MQTT and it's written in Rust. And you can also ask for calibration or standard calibration, which we do something like 150 megahertz, or extended calibration for specific frequency. I mean calibration of the interlocks, because interlocks are just implemented as a very fast RF power detectors, and they respond depends on frequency. So you can ask us to calibrate for specific frequencies, so the dBms you enter during operation are valid. So they are really valid for certain frequency, and usually you are really welcome to you are really encouraged to calibrate yourself if you want to recalibrate yourself. It's easy. You can simply need to run some serial port commands or MQTT commands to calibrate. And you can also order with any number of channels. Not everybody requires 8 channels. These booster amplifiers, they are quite complex devices. The designs which are on a GitHub is just a design. Of course, you can produce it, but there are a lot of catches in between, especially how to assemble mechanics, how to assemble cooling, and of course, calibrate and test everything. So every piece of amplifier order from Creotech comes with its own test report. So we measure several during test we measure several aspects like linearity, like so you can clearly see where the one PD point is. While you can also have a full frequency response at certain power. You can also ask us for another measurements if you need for your own setup. You simply change the PTS settings and can do characterization in slightly different conditions. And this is the output, the points which are tested automatically during each production tests. The booster is quite complex device. This is the block schematic. It shows 4 channels for the moment. It was designed in mind to build a new version of it. I mean, versions with different output power, with different cooling methods, with different frequency responses. That's why all it's heavy, massive, but it's also very, very stable. Due to its mass and in thermal inertia, it's very stable. If once you power it on, the fans hardly ever spin, and people are using for very, very precise measurements, for example. And it has a lot of protection mechanisms. All the voltages, currents, biases are monitored. You can run QTP broker and monitor all this aspect. This is important in case when you are doing long-term study of your setup. So you need to know all the drifts, all the parameters changing if you want to characterize well your optical setup or whatever you're building. This level of diagnostic is simply essential because you can get very deep insight into every aspect of your control system, not only treat it as a black boxes. And we are now currently developing a liquid cooling option. I'm not sure if it's going to look exactly like this. This is our first approach. In the parallel, we are studying another approach with common cold plate and individual and modules attached to it. So we study 2 approaches. I think we will make this prototypes till the end of the year, and then of course we will need to make a production version, but it will take several months. So I cannot exactly promise when it becomes a product. But if you are designing your new setup, when your vibration level is essential, you can also contact and we can simply say more about availability of this version. But it's not a product yet. It's mainly, and of course later on we keep the same chassis. So once you would be able to upgrade your existing boosters to this liquid cooled version. We only change the mechanics of these modules. Rest becomes the same. And under the development, we're currently developing a single version, 2-channel version. It's nice when you need single channel, when you don't need any diagnostics, and you want to have a low distortion power amplifier with 1 watt of power placed close to your phaser or Urocool. This is the way to go. It's matched to Urocool. It has it's matched to phaser. This no distortion version. As you see, it's produced, but of course we are testing it right now and characterizing it. and it's not yet ready to order. And now in the parallel we are working on this low-cost carrier board for mini circuits and amplifiers. People use it in the labs, but when you combine this brick outside of the crate, it looks nasty. But in this way, you can simply place it to the board, which provides 12 or 24 volt or 30 volts power supply, thermal shutdown. Doesn't have any monitoring, it's just power supply board, and some people use it already. But it's not in product yet. We are working on it. And recently we developed 10 watt power amplifier with potential trapping with a modulator integrated, so for active trapping potential stabilization. So this is we are working right now. And we also have another products, quantum related in Creotech. We are working on a new imaging and control solution for quantum processors. So we have a camera dedicated to qubit readout, especially in a new setup when we have a 3D traps. So we need a lot of a large field camera, a lot in short feedback. So this camera actually makes signal processing in real time, and you can have a very short feedback loop using this camera. Essentially, the thing is that it's going to be integrated into Arctic, but it's going to use independent interface, with much lower latency. Probably PCI Express. I mean, from hardware perspective, it works for PCI Express, but you can run around the protocol on it. I think that's it. Thank you for your attention. If you have, I don't know if there are any questions. I think Pavel will start with his presentation, and then we'll go to questions. Yes?
Yes, thank you very much for the interesting presentation. And now we'll move on to Paweł Kulik, who is one of the main designers of Cassidy 2. So Paweł, can you please tell us something about Arctic software?
Right. Okay, I hope you can see my presentation right now. So my presentation is going to be a brief introduction to Arctic, and let's start. So what is Arctic? Arctic is an open source control system designed for quantum information experiments, and it's both software part and the firmware part that's designed to run on controllers is open source. It features a high-level programming language that helps to describe complex experiments, and it provides support for Sinara modules. Arctic was created and maintained and is currently maintained by MLabs, which is a company that I think started at NIST. So let's take a look at Arctic hardware architecture. First, we have a PC, which is running Arctic software, which is connected to the local network. Then we have controllers that are running Arctic firmware. Master controller is connected to the Ethernet and will connect to the PC. Satellite controllers are connected to the master controller via fiber optic cables using DRT-IO interface. And then we have extension modules that are connected to respective controllers. And as I said, everything, including communication between devices and electrical schematics, is open source. So you can integrate devices that you already have or maybe made custom for your lab. Also, as I'll say in a moment, Arctic is using Python as its language. So every device that can be controlled with Python, so for example, sending Skippy commands, so these devices can also be controlled from Arctic. So anything else that you have in your lab that has a interface that can be controlled from your PC can also be controlled from Arctic. And these devices connect directly to your experiment. So they may control and read out camera, PMTs, provide signal to AOMs, etc., etc. Okay, so what does Arctic software supply? First, we can see graphical user interface, which features programmable applets that for each of the experiments can provide you with a real-time view. And we can also see a window which helps you schedule experiments with some specific parameters. The scheduler may be used to submit many iterations of your experiment, perhaps to gather some data and do some analysis on it, perhaps to schedule many iterations with varying parameters. And in between those iterations, you can also schedule, for example, a calibration run every hour. Arctic supports Git to track changes in the experiment code, and the database is used to store experiment results, which is also tracked with the commit of the of your experiment code. So you are able to go back to it and maybe recreate some conditions that were interesting and recheck something. And also Arctic provides custom gateware and firmware for controller devices. So now let's look at Arctic experiment code. So as you can see, it uses Python language, and the experiments are divided in 3 stages. First, there is a build stage, which doesn't have access to the real-time controller. In this stage, you can declare devices that will be used. You can calculate, you can provide some parameters that may be called from the graphical user interface and changed and iterated upon. And in this stage, you can also pre-calculate some variables that may depend on parameters. So for example, that this may be the amplitude of the signal or lower and upper bounds of frequency scan, things like that. They may be pre-calculated before they are sent to the FPGA. So next is the run stage. This is the only stage with access to the FPGA, and all functions which are decorated with this add kernel decorator are compiled and run on the FPGA. Operations on the FPGA are executed in a hard real-time environment. So exception is thrown if the controller device cannot keep up with events. And there is a remote procedure call link between the PC and the FPGA. So you can call functions from the PC to execute on the FPGA and vice versa. So what happens to this code that you write to run on the FPGA? First, it is compiled. Compiler may apply some optimizations to this code. Then it is sent from your PC over the Ethernet to the master controller. Master controller calculates and goes through the event queue and sends signal to devices, either to its own devices or it sends events to be executed on satellite controllers, which control other devices. And from the point of view of your code, this happens transparently. You don't need to worry about which device is placed on which controller. You may only need to take into account some delay that is deterministic. And in the meantime, master controller and PC maintain an RPC link. So for example, if you are debugging your code, you may call, for example, a print function from the FPGA, which will run on the PC. This is the simple example. And the last stage after your code on the FPGA exits, there is an analyze stage. In this example, I didn't have any data to analyze, but in this stage, you can run data analysis and save results to the database. And when you are using scheduler, build and analyze stages of different iterations are run in parallel with the run stage of current iteration, which pipelines the execution of many iterations. So what can I do in the FPGA with this code that's decorated with the add kernel decorator? Here you can use a subset of Python. You can use conditionals. You can do loops. You can iterate over lists, for example, which I'll show in a minute. You can throw exceptions. You have access to the timing commands, which provide you with 1 nanosecond timing precision. You can do some operations in parallel. You can pre-record sequences of events. And as I said, you can do RPC calls. So now for some examples of the code. Here we have a simple delay and for loop. This is the code that happens on the controller. In this loop, we are setting increasing voltages on 32 channels of Fastino DAC module with exact 100 microsecond delays in between. So this is a simple example. Now something more complicated. Here we have code that also sends signal samples to the DAC modules, but now we iterate over a sample list and introduce some delays. So this means that the DAC module will play back the signal that we sent to it. First, we take the current value of the time counter here. Then we do some operations. Then we set the time counter with the respect to t. So it's t plus some nanoseconds. And then we do some operations, and then we set the time counter again. So this means that the update operation that's in the lower half of the code will take place exactly after 256 nanoseconds. And the next iteration of the code, remember we are iterating here, will take place exactly after 392 nanoseconds, which will allow us to have predictable updates of the DAC module with stream set to 0.55 megasamples per second. And this declaration, this block of code with parallel, enables me to set output on 3 modules at the same time. So now we have an example with the DDS module. In this example, I had 2 Urukul cards, each with 4 DDS channels. First, we have a build stage in which we declare devices using some list comprehension. Then we have a run stage. First, I initialize the devices, looping over a list of devices. And then I set 25 megahertz output signal using also iterating over devices and using my function, which sets the frequency, sets the attenuation, and enables the channel. So Greg has shown you and explained in detail what devices we have and what are currently under development, and all devices that are sold by Creotech are supported in Arctic. So if you want to learn more, I think the best place would be to visit Arctic Manual and see the code for yourself. Since it's in Python, it's very approachable. You can, if you have any questions, you can ask them, ask here directly, or you can also visit MLabs forum if you have any trouble with your experiments. So thank you very much, and I believe the Q&A session will now start.
Exactly. Thank you, Paweł. Thank you, Greg, for your presentations. I am Przemysław Kowalski, and I will be moderating the Q&A session. So we've had a couple of questions. I will probably start with the first one. I've seen that Greg has already responded to it on the chat. The question was, do we know if there are any low noise current drivers for coils or lasers in development? And I don't know, Greg, if you would like to add anything to the link you have just sent in terms of the answer for this question.
We have a project which is called IARTIC. We develop low noise laser based on the frequency stabilization using Bragg grating. And for this purpose, we developed the dual channel low noise laser driver, which supports two channels which can work with common anode and common diode, common anode and common cathode lasers, and also measure the embedded diode, photodiode response. And it's no low noise. It means it's 18-bit DAC and yeah, a lot of interesting things. It works as a mezzanine for stabilizer. This driver. Yeah, you can look at the designs at the repository. If you have Altium, you can use also Altium online viewer to look at it. But as I said, it's you just have prototypes. We are testing with optical packages, and with this laser. We also developed laser module, but it's work in progress. So you need to be patient before you can buy it. I think MLabs also developed some much simpler laser driver. I saw it on the repository somewhere, but I cannot trace it down. It's a very, very simple device, EM form factor. Once I found out, I will post where is it. But I don't know. I don't know if it's supported by Arctic. I saw some design. I don't know status of it. We can, if there is interest, we can look at it. We can try to commercialize this project if it's sufficient. Yeah. So write down what you need it for, what are requirements, and we see what if there is enough interest from clients, we can push more efforts into development of such a driver.
Okay. Thank you, Greg. And the question was asked by Kai Miller. I believe, Kai, that if you can provide us with some more information on the context, then we would be happy to actually collaborate further and see whether it makes sense to actually commercialize this kind of solution. Okay, so the next question will be in regard to software. It was asked by Leo Walls. And the question is there a way to have a continuously running experiment where new values can be sent to the kernel while running? It's probably to Paweł.
Okay, so as Kai Miller answered in the chat, I haven't done that myself, and I haven't seen that. But I think using RPC and some continuously running loop in your FPGA would do the trick. Also,
Okay.
if you are running, for example, SU server, then you have a continuously running stabilization loop, and you can send experiments which can update running parameters of this loop while it's running. So it also somewhat depends on the gateway and the exact thing that you are trying to achieve.
Okay. Thank you, Paweł. Leo, if it doesn't answer your question, just follow up and we'll try to keep answering further. All right, so the next question from Etienne Woody. Is there a reference for the RF power stabilization feature of the standalone RF amplifier?
Is the reference for what do you mean a reference? The GitHub repository, yes? Yes, I can place it down. RF amp, oh, it's here. Okay, here.
Okay, so there is a reference to the repo, and because the question was about the reference for the RF power stabilization feature.
No. It's a different story. I talk about we write about we build. We are working on such a solution. It's actually it's my student at the university. So we have a ion trap which we purchased recently, and we are designing an amplifier which 10-watt amplifier which is able to drive up to work in VHF range. It's on a repository in the discussion session so far, and this is very early development. So I only mentioned that we are working on it. If you have, I can place an issue where we discuss all these requirements, etc. So it's here. So if you want to join or interested in it, so yes, we have two applications. One is this stabilization of RF ion traps. Another is stabilization of this antimatter traps. So we have two applications for the two clients for the moment, which have very similar requirements. So yes, it's going to be very high linearity amplifier with very low noise, phase noise, and also stabilization features together with stabilizer and dedicated RF high stability RF detector. We are targeting 1 ppm stability of the amplitude.
Okay.
So if you're interested, you can just join discussion when we can see what we can do.
Okay, thanks, Greg. Actually, I will ask you one more question, and it's out of the order of questions that have been asked, but it kind of touches the thing that you actually mentioned now. So the question by Team Bosain is, can we access prototypes for modules that are currently under development and or help with their testing?
Of course, yes, you can. Testing is very welcome. So the more people are testing, the better. The sooner we get the product. So we have limited number of prototypes, but of course, if there's interest, we can make more of them. Sure, of course, just contact sales, contact me, and then we can see what we can do.
Exactly. So what we could recommend, there's probably no process in place that would be available on the side of Creotech, so that you're just following the testing process or like the pre-access for the modules. But what you can actually do, you can contact us at sales@creotech.pl, and then we can follow up with you on what is possible to be tested. And it
so essentially you get a module without full support, without warranty, and to have it as it is. Because there are some hidden feature, hidden bugs. Yeah, of course, this is so you take some responsibility for what you are buying actually. But of course, there's also such option. We have several, for example, for waiver modules for these FMC carriers. We have quite a lot of them in our labs. So if they are available, so yeah, we can use them for tests.
Perfect.
Also, you can influence the design stage, since all the design is happening on GitHub openly, and actually the parameters of the devices are also discussed on GitHub. If you have any specific needs, you can just go to GitHub/Sinara-HW, and there you can see devices, you can raise issues with them, and also you can help develop them, or maybe check schematics for bugs, etc.
Yeah, any contribution is welcome as always. So thank you, Grzegorz and Pavel, for this one. The next question from Coral Westerby. Hey, I wanted to know what options are there in Arctic for high precision, low rate digital IOs, mid-10s picoseconds edge generation, and time to digital.
Okay, we developed the time to digital board. It's on a repository. It's 16-channel TDC. I don't remember. It was 8 picosecond. The sigma. We use it for MCORT experiment. It's supported actually by Arctic, but I don't know if it's already in the Arctic. We used it with Arctic at the university. It wasn't commercialized. I can give you the link to the repository. Let me see. One moment. I will place down the link to the repository. Pavel, do you know you were involved in this project, or it was somebody?
With TDC,
Nicole.
yes.
About the pulse generation, yes, low rate digital I/O. I mean, 10 picosecond edge is not. Yes, it's a challenge. You want to generate it with standard logic, but what we do for such a high rate generation, we use gigabit transceiver. So we essentially take gigabit transceiver and treat it as a high-speed serial to parallel or parallel to serial converter. And you can use costly transceiver or fast of this EMF MC carrier transceiver as a high-speed I/O, and we are using it either as a TDC or as to generate high-speed pulse trains. And this is quite easy because you just take gigabit transceiver from Xilinx, disable all the features like 810 encoding, and disable all this clock recovery and stuff, and then it works as a standard shift register. And you simply dump data, and they appear at the output. And 10 picosecond is yes, it's visible. You need to put some LVPAC driver on top at the output because you don't want to expose this transceiver output or input. So if you are interested, we have two projects like this at the university at the moment. One is actually in Creotech. We are building high-speed DACs because we don't for quantum key distribution, we don't need a very high amplitude resolution. We need something like 8 values. So we simply take a gigabit transceiver and put some R2R drive, the resistive ladder to make a DAC. And another experiment we are for ALICE detector at CERN, we are using transceivers as a TDC converter, where we have quite interesting results. I think we're able to achieve 17 picosecond accuracy with a very low noise. Essentially, the noise is the bin is size 17 picosecond, and the noise is also 17 picoseconds. So it's very stable, and we do it with gigabit transceivers. So it depends on the. I think we have some paper on it. I can send you some paper. Just write me down, and I will give you some details. But we don't have it at the moment as a product. We have this TDC we have a few prototypes. We have it tested. These prototypes have. I will look for them and give you a place in a moment. I will place on the chat. I will place a link.
Okay. Thank you, Greg. I'll continue with further questions, and I'll just add one thing on top of that, which is quite important actually, is that if you're interested in something that doesn't exist, you can always ask us also at like any personal contact with Creotech or sales@creotech.pl, because maybe there is some sort of a prototype, something that has been tested or is being tested or is being planned, where we are actually looking for the contribution that you're asking for, which is testing or like co-development. So we're always open for any kind of collaboration like this, and you're really welcome to actually join us doing those. So yeah, so we're still waiting for the link from Greg. And actually, as we run out of the questions from the chat, we also have some frequently asked questions that are being asked in regard to the technologies we have just shown you. And what I would like to, okay, there is another question from Leo Walls. Which is a follow-up to the previous question. If there is a standard way to use the Arctic dashboard to send an updated parameter to a running kernel, example trigger, such as an RPC call. Because when it was tried, there was an experience that parameters from the dashboard, they are only set once during the build phase.
Yeah, so I think the parameters that so basically the parameters that are sent to the core device may be compiled, and if the compiler notices that these parameters do not change in this code, then it will probably use some constant values instead of them. So I guess that would you'd have to find another way, and I don't think there is a standard way to do this in Arctic dashboard. I think I think you can post an issue to the Arctic repository, and I guess if there is enough interest in it, then it will be worked upon.
Okay. Can you quantify enough interest?
Well, it's difficult because mainly MLabs is developing Arctic right now, and I know that they are doing right now some pretty important projects for Arctic. So, for example, they are developing distributed kernels. So I've shown you the architecture of the system with multiple controllers. In the upcoming version of the Arctic, there will be a way to run kernels that will be sent to satellite controllers and executed then. So, for example, in the satellite controllers, you'll be able to independently calculate samples that will be sent to the DAC modules, for example.
Okay, I had a freeze of the internet, but I hear you, see you now. So thanks for the answer, Pavel. As there is no further questions in the chat, I would also like to ask a couple of questions to you, Pavel, that are connected with what we have just shown over here. Yeah, the new developments always seem interesting. So yeah, fingers crossed for the team of MLabs to actually make them to the table sooner than later. So the questions that are usually asked in connection with the amplifiers that we have just shown you, or the whole Arctic infrastructure or the project would be, how long would that take, Pavel, from your experience, to build the full experiment with the use of the Sinara for like 10 qubits, and a rough estimate of timing?
Okay.
Actually, we are building something like this for 20 qubits right now, don't we?
Yes. So it depends if you get already assembled system from us, because we can supply you with an already assembled system, also with some example code to run, and also depends on how many people you have. And the calibration, I'd say for our team, I guess it would take like a month, 2 months.
How many people?
I'd say 3 people.
Okay.
Assuming that we already have the equipment in our lab. Yeah, I think that's maybe more quickly, but we have some experience with Arctic already. If you're going to learn Arctic from zero, I think 2 months is realistic.
Okay. Okay, so thank you for this. One remark to the participants over here, because we will be finishing soon, because we are left with 2 minutes of time. So if there is any other topic in regards to all those things that have been mentioned today that you would like to learn, and you think that having a webinar on those would actually be beneficial, just please post it on the chat as well, because we don't really want to stop on the first webinar. We would like to continue spreading the knowledge on those products. So if there is anything particularly interesting for you, then please drop us a message so that we know how should we prepare the further events like this one. And Pavel, the next question to you. So you mentioned that if you have the system assembled, so is it also possible for us to provide some sort of the user interface for the system? So like, how far can we go with the software support?
Yeah, it shouldn't be a problem. So far, no one asked, and that's why we didn't do it. But I think if we might need to maybe include this in on our pages, that we also may support supply such a user interface already pre-configured.
Okay, that's an important remark. Thank you. And the last question I have from the frequently asked here is actually it's two questions, but it's connected with the amplifiers we were discussing earlier. It is, so are those amplifiers only dedicated to the Sinara experiments, or are they like a generic use thing that we can benefit from in any other application?
They are not related at all. I mean, they were created within the same, for the same clients, for the same customers, for the same setups, but they are independent boxes. They don't need Arctic. They are just put it on the table and press the button and start, and it works. If you want to have some logging, you can connect to any. You can connect serial port, and you can connect over Ethernet. You can run a MQTT broker, but otherwise it's people from for various fields like atomic, for example, atomic experiments that are using them without Arctic at all. So yeah, this is completely independent devices.
Yeah, I've also seen Sinara devices, the extension modules used independently without a controller. So many of them have a simple SPI interface that can be interfaced to existing devices. So for example, Uruku, so the DDS module was used in that way, and a paper was published with it.
Okay, so thank you, gentlemen, for your answers. I believe we just got to an end. So Zofia, you need to unmute yourself to close the event.
Yes, thank you very much for attending this webinar. I hope you learned a lot. And once again, thank you for joining.
Thank you very much.
Thank you.
Bye bye.